All right, let's continue with the second learning objective. But in the first learning objective, remember that we learned how to find a related rate. Now we're going to use the related rates to solve real life problems. A quick heads up for you before I start. Most of the problems in this section are word problems. That means you're not provided an equation directly. So you have to convert the word problem into a problem where you can write an equation for. For that reason, just get used to that. And I'm going to give you the guidelines to solve related rates problems first, and then I'm going to go into a real world problem. Hopefully, you're going to enjoy the application of the differentiation for that problem. All right, so in the guidelines, what do we have? Let's see. We have the first item here. So first off, when a word problem provided to you, you're going to identify all given quantities and quantities to be determined. So you have two different things to sort of like identify. One is like what are the given quantities, and the other one is like quantities that you're supposed to determine at the end. And obviously you can make a sketch or and label the quantities. Okay, so you can just call something X, call something Oz, call something your name, something like that. All right, let's check out the second item. Well, we're going to write an equation involving the variables whose rates of change either are given or are to be determined. So remember the original equation business in the previous video. So we need to have an equation to start with. And obviously, you're going to write down the variables that you named in the first step. And maybe some of the rates of change are provided to you or some are to be determined. All right, in the third step, we're going to use the chain rule, obviously, to implicitly differentiate both sides of the equation with respect to time because all of the variables are functions of time. And in step number 4, after completing step number 3, after we're done with implicit differentiation, we're going to substitute into the resulting equation all known values for the variables and their rates of change. Because in the word problem, you may be provided certain quantities, so that's the time to substitute those values back into the related rates equation. Then obviously we're going to solve for the required rate of change. Whatever the question is asking, we're going to solve for that related rate. All right, let's apply all of these 4 steps to a real world problem. We have a pebble dropped into a calm pond. Obviously, that's going to cause ripples distributing all over, right? And they're in fact in the shape of concentric circles. We have the radius r of the outer ripple, and that is increasing at a constant rate of 1 foot per second. Okay, so we already have a variable named as like r, and we're given its rate of change in time. In other words, we're given dr over dt, 1 foot per second. Let's keep reading. When the radius is 4 feet, at what rate is the total area A? Here's another variable provided to us in the question statement. So at what rate is the total area of the disturbed water changing? So when you talk about rate, that means you're being asked dA over dt. Okay, so when the radius is 4, I'm going to try to find how fast the area of the outer ripple is changing. All right, so now in fact the variables are already provided to us, r and a. So all we need is the relationship between a and r, and a is the area of the circle, and we know how the area is related to its radius. So we have the relationship a equals pi r squared, and that's what I'm going to use in the next step. All right, here we go. This is a equals pi times r squared. So I have two variables again, a and r. They are sort of like related to each other. So this is going to be my original equation. All right, let's try to digest the steps so far. We have the variables named. So we have a and r related to each other. We're going to find dA over dt along the way. We know that. And also we have the equation. So now we can jump all the way into the third step, but let's also write the other data provided us in the problem statement. So we have dr over dt equals 1, and we're going to find dA over dt whenever r is equal to 4 feet. So now what I'm going to do is to take the derivative of the equation here, and we're going to use the chain rule. Here we go. So the left-hand side is just dA over dt, and the derivative of the right-hand side is pi times the derivative of r squared, okay, r squared. And there comes the chain rule. So by the way, we just pulled out pi because pi is a constant. We can always pull it out, right? Pi times 2 times 2 down the exponent. We subtract 1 from the exponent, so that becomes r to the power of 1, which is r, times the derivative of the inner part, and that is dr over dt. So in short, this is equal to 2 pi r dr over dt. All right, so now we're going to determine dA over dt for r equals 4 and dr over dt equals 1. Okay, so here we go. I have 2 pi r times 1, and it becomes 8 pi feet squared per second, because we're talking about the rate of change of the area. Area is coming with the unit feet squared, right? Feet squared per second. So if r is changing 1 foot per second, then the area of the ripple, the outer ripple, is changing this fast. All right, now let's look at certain verbal statements in word problems and how we can convert those statements into mathematical models. Let's just read it out. So the velocity of a car after traveling for 1 hour is 50 miles per hour. So the velocity is the time derivative of the distance traveled. So naming x to be the distance traveled, which is a function of time. Dx over dt is going to be the velocity of a car. So it's going to be dx over dt equals 50 miles per hour when t equals 1. See, like t is not provided to us, x is not provided to us. We sort of like made up new variables so that we have a good mathematical model for this statement here. In the second one, let's say like water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. So cubic meters is, you're talking about volume, obviously, cubic meters, meter cubed, right? So the rate of the water being pumped into a swimming pool is cubic water per hour. So then I need to define a variable for volume. Here we go. So the volume then is changing in time because you're pumping in water. So you're talking about dV over dt, and that's provided us as like 10 meter cubed per hour. So again, there was no mention of the variable v in the problem, so we made it up. And for that reason, we came up with dV over dt, which is the rate of change of volume in time. All right, in the next statement, we have a gear revolving at a rate of 25 revolutions per minute. That's a rate. So revolution is somehow like related to the angle of revolution. Here we go. I made up a new variable, theta, which is the angle of revolution. And the rate of change of that is represented by d theta over dt. And that is, in fact, 25 times 2 pi, because we want to write that down in terms of radians. That's what calculator recognizes, right? 25 revolutions means like 1 revolution is 2 pi. So we have 50 pi radians per minute of rate for the change of angle of revolution in time, okay? And the last statement, we have a bacteria population that's increasing at a rate of 2,000 per hour. So that means 2,000 people per hour, or 2,000 bacteria per hour. So then if I call the number of bacteria in the population to be x, then the time derivative of that is going to be the rate of change of x in time. So that's in fact 2,000 bacteria per hour. As you see that in each statement, there is no equation or new variable provided to you, but we made up sort of like mathematical models to make the problem ready into a related rate problem. And my final comment here is that please check out the geometry formula card in the Blackboard modules, because in certain cases you may need to find the volume of a tank, or you may work with an ellipse, you may work with a right triangle, and others. Please check the formula card and have it in your hand before you head to the REST station videos. So to wrap up my final words, please go ahead and start watching the REST station videos. You have really like cool problems in the REST station videos. Here is one of them. So x and y are variables, and they're both functions of time, and they are so like related to each other through this equation. And you're asked to find certain rates by using this equation. In another example, we have a point moving along the graph of the given function, which is y equals 1 over 1 plus x squared, and we're trying to find at what rate it's moving. So this is also another good question. And if you just click on the watch the video here, so you can easily watch the video on YouTube. So just saying. We have another application problem. It's completely a word problem. So we have an equilateral triangle, and one side of that is increasing at a rate. The question is asking how fast the area is changing. So this is an awesome application problem. Also in REST station videos, you're going to find this exercise, which is, again, an awesome application of related rates. It's an air traffic controller problem. Please watch this video, because it's all about two planes flying in different directions, but if air traffic controller doesn't break in, they would have an impact at some point. So you want to know when the impact is going to be. Please watch this video as well. All right, we're closing the discussions about two learning objectives. Thanks for watching. I'll see you in another video. Bye.